Okay, so this is the Q&A session. I have the questions in my email and also in my Facebook. So I will try to tackle those questions one by one. Okay, let me open the email. Uh, okay, this is my email. Where is it? Okay, so it is from. Okay, I'm looking. Okay, I'm just. Yeah. So let me just cut and paste here. Because it's on my email, so it might be accidentally show you a few things that it's not, you're not supposed to see it. Okay, so this is the first email that I got for the questions. Okay, thank you. Okay, you're welcome. Okay, pumping stations, them running water today. Okay, uh, overflow, water flow over a bulkhead, and this is a sketch. Yeah, in the textbook. Okay. Okay. I think this is a question. I'm just wondering, this is a question. I'm just wondering if it is possible to define the inlet velocity not being constant. See that attach. Okay, and he attached like a PDF. Okay, I think this PDF I can show it here, a different window. Uh, okay, that is one question. Uh, uh, what is the first question? Okay, today. Okay, flow over bulkhead. So that is actually one thing. It's the same in the same sketch. So here, this example, I think it's actually covered already because we have seen yesterday how to manually control the water level, right? So we can control the water level and we can put the rigid wall, whether we want to make it uh, FS coupled with FSI or not. And yeah, we seen how to make different lines. Okay. So for this one, I believe it should not be a problem.
No, you covered it yesterday already.
Yeah.
Yeah, yeah. Thank you.
Okay, welcome. And this one also I think is covered because
Yes,
we did the pressure. So I
yes,
think for this one is okay.
yeah. Perfect.
All right. Now for the second email. Non-slip condition. Okay. Let me try here. Okay, now we'll just copy paste. There is no attachment in the second email. Where is that friend? It went here. Okay. For wall of the pipe, then there is no slip at all. Is it possible to specify a friction number so that there is partial slip? So an intermediate form of free slip and non-slip. I can't find it in ICFD counts. Okay, as per my knowledge, this is not possible because even from my learning of fluid mechanics and my knowledge is not actually that deep, there is not that is not possible. I mean, physically also it's not possible. If it is some sort of a keyword to do this, then I'm not aware of. As far as I know, that is not possible to make like between non-slip and a free slip boundary condition. Okay. Uh,
Okay, thank you.
okay, no problem. Okay, as for the fourth option, I think we can, for the second question here, we can use a function, but also we can always consult our user manual. Okay, so here, the ICFD key, ICFD, it is here, prescribed velocity. I hope there is more information. Unfortunately, no. It's the same as here. Uh, okay. So here it says about the, yeah, about the define function. So if we want the one that we just seen in the sketch, we can use the function.
Yeah. Thank you.
Mm, parabolic. Yeah. Oh, I did something disappear. No. Uh, parabolic. Okay, so if this is about option number 4. Okay. Parabolic, it's a power of 2, right? So if it is option number 2, or option number 4, it will be parabolic. It will follow a parabola. So the power, it's x power of 2. But if we want more control over the curve, then we can use define function. Okay. Now we have one last question in the email, and then I will go to the messenger. 3D problem simplified to 2D. The steel cylinder 5 height that is clamped to the foundation. For the 2D simulation, can we cut the top part 1 meter height loose and then compensate for the cutting? We need to add horizontal spring stiffness. To view that, is it possible to add these two springs in the 2D model? Yes, it's possible. I've did that one before, but I do not have the reference file, unfortunately. It should be similar to what, I'm not sure if you should, I think you have joined the previous workshop where we use the spring elements. It should be the same. So, wait, did I disconnect? No. Okay, so it should be similar to the previous example where I did the spring, remember the road and the bridge. So, but here maybe we will try to do that because it's just adding one spring element and it should be fine. And it is from the third day, right? So it is example 3, and it should be VIV because we want the thing to move. And here I will just open this, and I will save as a different separate keyword. All right. So here, what I would like to do is to add the stiffness. So I can go to node and create, and what is the position? -300. So I want to make -3 and 1 on the top here. So y should be, it's 5, maybe 3, 3. Let's see, where does it go? Oh, it's too high actually. 0.5. Yeah, this is fine. And then I will go to element generation, and then go to beam, and then go to this discrete here, discrete by 2 nodes or 2 node set. So this is the first node here at the center, and the second node here, and then create, and then accept. And of course, we need to fix this top node. So I can go to here, or you can go to F4, click here. So this is the node ID. Since this is a small model, I can do like this. Go here to node, and the last node that I have. Yeah, this is the node. So I can just constrain everything here. And actually, to be more specific, I need to constrain in X and Y because we do not have Z. But if I put also 7, which means I constrain even Z, then that's fine. So this node is actually now constrained, and then we will need to define the properties of this spring. So where I should go to mat elastic spring. It will be down the list now here. Spring linear. Not seat belt, but it's elastic spring. Material number 2. So this is spring. Okay, I will put this is just a rough number, 500 Newton per meter, accept. And the length here, it does not matter because this is a linear or an elastic spring. And of course, I can put a damper, and we have seen in the previous example how to put the damper. Okay. Okay, wait. Is it someone that wants to join or what? Okay. No, not that. Okay, so here now the section spring. The section, and where is it? I believe it was spring damper, new. We can just put it default, but this is a translational. If I want a rotational, then I put DRO equal to 1. So here, spring section. Step done. And here, what is that I want to do next is I want to assign this. So this is spring section, spring material, accept, and Control S to save. Do not save as subsystem, save as include VIV with spring. Or I can just call it VIV with spring. Okay. So here I can terminate this for now. And then right click, refresh, VIV with springs, and drop here. It should be working. I've tried this before. I mean, when I say works, meaning it works with no error termination. I do not have the reference file. It was 4 years ago, so I deleted. That's very sad. Very unfortunate. Okay. So here it's just loading. Did I open the correct file? Okay. Wait. I'm running. Wait, where is the model just now? Oh, I'm running this one, right? I'm running include. No, I should run stop this VIV with spring. Yeah, I was running the wrong model. So this one you can close it. This one, just leave it here. because we are still working on it. Okay, this is just let it be. And then let us try to run again. Okay, so it is working. The problem here, I think it might be a problem, not a problem. We might need to change the implicit dynamic keywords because to cater the spring, because the spring is very deformable. So we might need to change the something in the implicit keyword, implicit control, implicit general. So here, do we have any result yet? We do not have any result. So you can see this is the spring element. And this is just an LS-DYNA thing. When you open the, when you run the file, when you open the post processor, the spring element will show nicely. But when you open the result, it is always a straight line like this. So as far as I know, there is no solution for this visual, I would say not error, just it's just a misconvenience. Okay, so here we can see it is running. Do we have any D3 plot for now? Or no, not yet. Okay, so when we add a spring, I believe we also need to add some sort of damper. Okay, so when we have a spring, it's also good to have a damper. So it just that is just running in the background. And wait, why is not? I think maybe I need to. I downloaded already, but still doesn't open. Okay. Yeah. So we add the vertical spring. We can add the spring in Y. As I mentioned, the length of the spring doesn't matter. It's an elastic spring anyway. And this case, how it is different from our previous case. The model that I have created without the spring is like the case of the 3D. We have the flow and the whole pipe is vibrating. The whole pipe is just vertical. It does not bend anything, and it just moves as a rigid body. So that is actually the case that we solved in the third day when we did with no springs. If it is bending, then yes, you need to add some spring to compensate for the fact that we cut the structure. Okay. All right. So that is for the PDF.
Yes, thank you. Thank you very much.
All right, no problem. Okay, the question of the turbulence actually is very deep one that is hard to answer based on this workshop. Mostly turbulence is important with when we have high Reynolds number. High Reynolds number meaning we have high velocity and the viscosity is low. So if that's the case, then yes, check choosing the right Reynolds number is important. From my experience, when we have like low velocity, then the turbulence model number one, the number one should be enough. ICFD control turbulence, which is the K epsilon, runs K epsilon. So this is okay when we have low velocity. I mean, not not low velocity, when the turbulence is not very high. Okay. And by the way, if we do not define this keyword, then the software, the result will be slightly different. From from the examples in this workshop, I tried to turn off to run with and without this control turbulence, and the result is there, but it's not that much, which means that the turbulence exists, but it's not very high. Okay. All right. So I think we can move to the next group of the questions. And here is the next group. Let me check here first. Okay. I'm checking the Facebook, okay? Do I have another? Okay. No, this is the only thing that I have on Facebook. Vibration or irrigation, which one cleans better? Okay, this is an interesting case, an interesting simulation to do. We have two cases. So we have, this is inside, I think, inside a structure, inside the tooth.
That's a
And this,
tooth, yeah.
yeah, and this will vibrate. And inside we have SPH. And here is the first question: how should I define the boundary condition for vibrating linear or circular stroke pattern? Okay, first of all, it depends on the actual movement of the structure, and depends if you want to reduce it into 2D simulation. If you want to reduce it to a 2D simulation, as in this picture, I mean, we can see here is like a 2D cross-sectional shape, then it's better. I mean, you have no option but to make it linear, meaning going back and forth. Okay. For if it is a 3D and you're looking from the top and this is actually rotating, then you need to make it define two boundary conditions: prescribed motion rigid in two cases. So one will be the x coordinate or the x velocity. The second will be the y velocity, and they will they will be defined together such that it rotates. Okay. I do not have an example of that, of course.
Yeah,
That's
how do we define the curve? That's what I want to know.
okay. So
Just one or two is okay. The keyword, I want to see the keyword.
okay, I have something similar in idea, but of course not the same.
Yes.
It's here. What's that process called? Incremental sheet metal forming. Okay, is this the result? Okay, I have a video luckily for you.
Oh, thank you.
So you can see this tool is rotating.
Yes. I want to do something like that.
Yeah. So basically, I'm not sure if you can define like a radial coordinate system, but in my case, it was simply just X and Y. Okay, I do not need the mesh. Oh, I do not have the mesh file. So define a curve. So I have the X and Y displacement. So this is actually the displacement, and this is the Y displacement. So it's just something like this. And if you have some good background in math or just basic math, then you can just know it's like the X function, the what you call it, the sine curve and the cosine curve.
Mhm.
Okay, let me see Desmos. Okay, so this is and we have y equal to sine x. So this is only what you need to do, a simple curve. and you will get a perfect circular motion if you define the x coordinate like this and the y coordinate like this with this function. Okay.
Oh, okay.
Yeah.
That's basically what we need to do just to define the motion, right?
Yes. So
So
for yeah,
mm,
exactly.
mhm.
So let me can I put a polar coordinate here? Okay, x square plus y square equal to 1. Okay, we have the circle. Good. So we have the circle, and then okay, you can see the circle. When
Mhm.
when x equal to the maximum value, y is 0, right?
Mhm.
When x equal to 1, y equal
Yes.
to 0. But and here you can see what for one curve the value is 0, for another curve the value is 1, and then it goes down until it reaches 0. And when the second curve reaches 0, the first curve reached the maximum value.
Ah,
So
okay.
it's similar to this. First the x0 y0, and then using a very nice curve it reached this point, and in this point the y is 1 but the x is 0. So it's just like this. Okay, and you can use a define function as we did yesterday, but just keep in mind that the angle that you put is actually in radian, so you need to convert it. Okay, you need to multiply something here. Okay, and in that case it will be the time, so you need to uh, just go to define function. Where is it? I have did that in one of my previous workshop, but I do not know which one, so it will take some time to search for it. So define function, so we just put here equal to, or just no need to put equal, just cosine and time multiply by pi divide by 180 to convert this from to convert what's inside the bracket from radian to degrees. And time is here is the simulation time, of course.
Mhm.
Yeah. So that's all what you need to do.
Oh, okay.
Yeah.
So thank you.
Okay. So that's the first question. The second question, uh, I'm not sure if you can use SPH. This is water. Okay. Yeah, using SPH is good for modeling debris. But I would recommend to use ALE actually.
ALE.
Yeah. Especially with this one, because we have the inlet. Okay, the inlet, again, it depends on your boundary condition. What's you are inputting in the machine, and I believe is actually pressure, right?
Yes, the
Yeah,
pressure or displacement.
displacement.
It's like a serene.
Oh, okay, okay. Oh, okay, okay. So it's manual. It's not like you have a machine. You just press with your
No,
hand.
yeah, we just press with our hand.
Oh, okay. Then it should be like you can estimate the velocity, and you can just put a velocity there.
Okay, we just add the velocity. I mean,
Yeah,
at the tip. That's it.
yeah, yeah.
Okay, and then the water will come out automatically.
Yes.
Okay, then how to?
Okay.
Yes,
Wait, I
that's
have
it.
few things here on my channel actually. This is water jet with LE, and this is with ICFD, and this is with SPH.
Ah,
Okay.
okay.
So for one good thing about using LE that you do not need to model the whole water volume in the shrink. Okay, you just need to model the tip, and you put the inlet velocity there, and the software will automatically understand that you have infinite amount of water. But if you are, yeah, and similarly to the ICFD, and actually with the with the SPH also is possible like that. There is a keyword called the define. I believe it is define SPH. Is it define? I'm not sure. Yeah, define SPH injection. So here you just need to define the velocity and the area, and okay, this is the node set and also the location of the injection. Okay, so I think yeah, this should be helpful to do the injection with the SPH. Okay, so you back to your question, you can put velocity. Okay, if you are using the SPH injection, then the velocity is just already there. It's already here. You can define the velocity.
Okay, thank you.
Okay, all right. If you are using ALE, then I think the video just now can be helpful. Here I used initial velocity generation. Yeah. Okay, so I think that answers the question, right?
Thank you.
All right. Okay, the second one. Mold material SPH, rigid body, soft tissue mesh or SPH. Okay, rigid body will move upward carrying the mold material. Mold material placed like material. May I know the suitable model for this? Any suggestion further? Pink and black. Okay. You want first we will answer the simple question. The material kind to stick to the body. How should I define the contact? Okay, we will go backward. Okay, the black is rigid. Okay, and the pink is deformable. It's a paste or
Yeah,
a
it's a
mold.
paste.
Yeah, paste. So what you can do, you can use constrained rigid body. Okay, I do not have any model here. Okay. Let me try to, do I have anything similar in shape? I do not have. Okay, so I will just create, I just show you the keyword. The keyword you can define from here. Okay, maybe I need something visual. Yeah, it's better if we have something visual. Here I can close this. And do I have any model open? No. Okay, I just need a full model. Basically a structural model. Okay, this is related to your case, a soft material. Instead of, did you ask about the, oh, you're asking about the
So
material. Okay, about the
yeah,
material.
but by the way, the phenomena, like the one that I'm doing, is included on the top right corner. I mean, the photo. That's what I'm doing. At top right corner. That's what that's what it is about. Yes.
Yeah.
But
Okay.
this is a 2D, so it's a symbol.
Yeah. Okay. So basically you are making something for the teeth. Yeah.
Yes.
Okay. So here, okay, first for the material. Okay, this is a similar example that something similar but not the same. It's a metal forming. And here is the result. Maybe a 2D result should be more visible. Yeah. So something like, but in your case, that's the one on the bottom is moving up. Okay, so here you're asking about the material properties and you're asking about the contact. With regard to the contact, you can use constraint, not contact, constraint, rigid body, or constraint extra node set. Okay, so here, this one, the number 3 is rigid. This is the tissue-like material, the paste material. You can go to here. I think simply define from here. Constrained node set. Is this the one? No, not this one. Extra node set. Yeah. Constraint extra node set. Create. And then click here. The rigid part is this one. The number 3, which is the one on the bottom. And I need to select the nodes. So select all the nodes at the bottom and then apply. So now these nodes will be connected to this rigid body here. Okay, so
Thank you.
yeah,
Thank you.
welcome. So this is about the contact.
So
Now
that one is not SPH, that's ALE, right?
it's not
The
SPH.
it's not SPH.
It will work with SPH as well.
Oh, okay.
Yeah, but this case we call it, this is a solid material. It is called EFG.
EFG, element free plugging.
Yes, correct.
Okay.
All right. So the material kind of okay. So this one is okay.
Yeah.
What is the suitable material model? Okay. This one, after you press, it will deform, but it will stick, right?
Yes.
What is the okay? I have something in mind that might help. Plasticine, LS-DYNA, since we are using LS-DYNA. Okay. So I think plasticine is like the Play-Doh.
Oh,
So,
okay. Yes, that's
yeah.
a Play-Doh.
Yeah. So I think the commercial name is like plasticine. So we can see from here what material model they are using. And I think they are using just simple plastic kinematic material model. Of course, we have more advanced material model here. Okay, let me log in. Don't copy my password. Oh, it's not even available for using my university account. Yeah, here. Here it is using just a simple material. Yeah, it's doing something like this also. We have like a mold and it's being compressed. And number 2 is plasticine. Just now, this soft material also are used in metal forming. There is some sort of metal forming material. It's called punching or soft punch. But here did he give the material properties of the soft material. This is the output from the machine. Numerical simulation. Okay. Okay. Okay, so you can see he is just using material number material number 18, I think.
18. Okay, that's
Yeah. Basically, it's just a simple material model.
Okay, material number 18.
Yeah. If you want a curve exactly like this, then material number 18 can give you. But you need, of course, to have the stress strain curve. The material here is red plasticine. I don't think that's the same thing that you are using. But the general behavior of the material of this sort of dough material is following this curve. Yeah, I want this curve here. Oh, okay. Sorry, I click on the wrong place. Oh, this is my own work. Funny, is it? Yeah, this is my own work, and I gave the reference number 47. Yeah. So you can see I've used plastic material number 0.24 for this work. Okay, so this is the article and material number, reference number 47. So here basically we are doing metal forming, but we're using plasticine instead of using actual steel, because that will be much easier. So the reference is here. You can see plastomeric test for plasticine as physical modeling material. And this is also, I think, is an open source. Yeah, it's an open source. So if you have the stress strain curve, then you can just use material number 24. Yeah, so you have all these curves. So material number 24 should be also a good option. Here he has different type of plasticine. He have white and black as well. Yeah. So material number 24, in which you need to just input the plastic zone of the material. The elastic zone, you do not need to input it in the curve. You just put you just input from the plastic zone here, and the elastic zone will be understood by the software from the elastic modulus E. Okay. So I think that's answered the question for the material. So material number 24. And yes, you can use SPH. And if you want to go with a 2D, then you do not need to use SPH. You can just use 2D with adaptive refinement. So that will be a better option in my understanding.
Thank
Because
you.
because you're welcome, because it will be much cheaper. Okay. So here, do I have a 2D, the one I have in mind to show you? Self-rivet. I believe this is the one. This is the article. This is a 2D. Yeah. Open the D3 plot. Okay. So it's metal forming again. It's not your case of something in the tooth. But you can see we have this material like this. Oh, I did not run until the end, I think.
But this is just 2D, right?
Yeah, 2D.
Oh.
Yeah, it's just 2D. And you can see here, you can see the mesh is actually alive. You can see the initial mesh like this is very structured. Everything is perfect square. But now, as soon as the contact happens, it will follow the value of the minimum and maximum value of the element size that I define in the keyword. Okay, and the keywords for that, I will just show you the necessary ones. Adaptive refinement. I think you did not join the previous workshop where I showed that, but that's okay. Part here for top sheet and bottom sheet, which is 4 and 5. We need to put number 2 to flag on the adaptive refinement. Okay, for part number 4 and 5. So we tell the software, okay, these 2 parts will have adaptive refinement, and we need to go to control, adaptive, and here is the adaptive size, the element size. Okay, so if I measure just now, it will be around 0.1. Do I have the results here? Yeah, if I measure this F2, F4, you can see is around that value, around 0.1. Okay, so you can see is around 0.1. And here is the frequency. So every 0.05, I do not know of the units here. Let me check. This is millisecond. So every 0.05 millisecond, the software will generate to you a new mesh. Okay. So that's only the 2 keywords that you need to activate this. And of course, adaptive option should be 8 because you are using plane strain elements. Okay, axisymmetric or plane strain elements. Okay.
Thank you.
All right, no problem. Okay. So that is for the material. Okay, I do not understand this. Which one caused less tissue displacement?
That's the research question.
Oh,
It's
okay.
okay.
Oh, so you want to do like a different design?
Yeah, I want to make some holes and then push it, and then maybe I also want to do without hole and check the tissue displacement. But we cannot do that on patient because it's unethical.
Yes, yes, of course.
So we can simply do it here.
Okay. All right. Yeah, I think this will be very similar to what you're having.
Yes,
Yeah.
yeah.
Okay.
Can I have that keyword, or like is it published somewhere?
I need to check first. Yeah, I need to check I need to check whether I can give you this file or not. Okay.
Thank you.
All right, no problem. One more thing about this file, I'm not sure. Oh, I closed it. What sort of elements formulation we used? Yeah, here because okay, I use 15. It's asymmetric.
Asymmetric solid. Okay.
Yeah. So if you use this one, then you are modeling half of the teeth, but this with the assumption that the tooth is perfectly circular. That's the meaning of asymmetric. But
so what do you mean by perfectly circular?
What I mean is, if you use that one, then
okay, the circular.
Yeah, you just rotate like this, perfect circular. Okay. But if that's the case, if that's not the case, then you can use like this plane strain instead. Yeah, you can use number 13 instead. So number 13 is like when you have like a let's say a box or a cube, and then you cut a very thin section of the cube, you will get a square. So if you're modeling the square instead of the 3D cube, then yes, you can use this 3D plane strain. Okay. And if that's the case, then you need to model the whole cross section, not only half. In this case, we are only modeling half, in the software will just automatically rotate because we are using axisymmetric. All right. Okay. There is a file that you can have it and it's available actually, but I'm not sure where to find it. Self Rivet LS-DYNA. Yes, this one is available somewhere, but I'm not sure where you can find it. Because if you install, oh, it's here. Yeah. Yeah. Yeah, so it's similar, almost similar. Or if it's the same, I'm not sure.
It is similar because we want to check the void here.
Yeah.
The void. Yeah, that's very similar.
Yeah, so I think can just have this one. Oh, sorry. I will just put in the chat box. Okay, where is it? Okay. This example manuals actually, it comes with the software when you install it. Okay, so now they are open, they are putting it here. I do not know if they did it before, but these examples are not new. It's sometimes when you install it, when you install the software, it comes with some examples, some documentations. The self-rivet example, it's also one of these examples that comes with the software. Okay. All right. So is there any questions? Any more questions?
No, I'm good.
Okay.
Thank you. That answer a lot of my confusion.
Okay, no problem. Okay. So remember the define function just now? We forgot to multiply by the magnitude. So if you put the function as I wrote it just now, the rotation will be only one unit length. Okay, if you want it to be bigger or smaller, then you need to put a factor like 0.1 multiplied by 0.1, the whole function multiplied by 0.1 or 0. Or by 1 or 10 to make it bigger or smaller. Basically, you might need to scale it up or down. Okay. Okay, I do not have a example of define function. I have, but it's somewhere here. I'm luckily, sadly, this function cannot search inside the keywords. But here actually, instead of like this one, we can look into the manual. Okay, the manual is really a lifesaver, but many do not use it. So define function. Oh, there is one question from you that I need to answer. Okay, so here is the define function. It gives you a lot of description. And here, as you can see, prescribe a sinusoidal x velocity and y velocity for some nodes. So you can see here, the function is like this. X as a function of t is this one. And here, this is the acceleration. As a function of t is this one. Or I think, I'm not sure why we have A here. Maybe it should be Y or Z, because here it says Z velocity. Yeah, I believe this should be a Z velocity. Okay. And degree of freedom 1 VAD. Okay, and here is another example. Okay, so this is apply hydrostatic pressure ramped up over a finite time. Okay, so it is similar to our function that we have did before in our example yesterday, but here it has some ramp up, meaning it will start from 0 and it will go until it reach the maximum value. But in our case, yesterday we do not have that ramp up, so we directly put this value, okay? Rho gravity reference minus y. Okay, we put something similar here. But in this example, he defined few things because he want to initiate the hydrostatic pressure gradually. Okay, he doesn't want to apply like a sudden gravity. Okay. There is one more example of a define. There is define curve function. Okay, sorry. What we are seeing here is slightly different than what we did yesterday. What we did yesterday is define curve function. What's here is define curve function. So define curve function, if you look at the example, I'm still not quite sure what is the difference with, okay. Define function is more general, but define curve function is like applies only for curves. Okay, so here, for example, this is an example for the syntax. Define curve function. So 0.5 LC9 multiplied by VM22 multiplied by 3. Okay, you can see here half is half. Ordinate, meaning the location, sorry, meaning the y-axis of the curve number 9, LC number 9. VM22 is magnitude of translation for velocity at node 22. And multiply 3, meaning power 3. Okay, these are just examples of how to do different things. This is the example of what we call it, the to put the sine curve here, and also here to define. Okay, there is one more function that I cannot find it here actually in the example. Maybe it's a different version of the example. Here you can see if you want to have a stepwise function. Okay, so when time equal to -5, this is a function, and if not, this is the function. Okay. Okay. All right. Another question from the same person is about the material model. For the material model, for hard material model, usually for rock type of material model, we do not use elastic. Okay, because matte elastic doesn't have. The question was about rock material. It has like more than one elastic modulus. It has elastic modulus for static, and for high strain rate, the value is different. This is for rock materials. To answer that, to consider high strain problems, we do not use matte elastic. Okay, because matte elastic cannot consider higher strain rate effects. So what we would like to do,
that's not my question, but can I ask you one thing?
Yes.
So matte material does not consider that does not consider high strain rate, right?
Matte elastic.
Matte elastic, yeah. And for the how about the material plasticity? Plastic MET24. Are they
Okay.
the same?
Okay. Both matte elastic 0.1 and matte plastic kinematic
Yes.
003. Okay, matte elastic doesn't consider the strain rate. Matte plastic kinematic can consider the strain rate effect, but it considers the strain rate effect only for the yield stress.
I see. Oh,
For the
okay.
elastic part is not considered.
So
Okay.
it's not suitable for the rock material. I mean, to use the elastic just elastic modulus or rock material.
Yes, for rock material, it's not.
Oh,
So it's not
I see.
suitable to use matte elastic.
Because I
Especially,
found something similar in ceramics too.
yeah, for those materials, we have like special material models. Okay, you need to go down to material above 100, 111, for
Oh,
example.
thank you.
Yeah. Or 110. Okay. Matt Johnson Holmquist ceramics. Okay, this has been used for, you can see articles using this, and it also considered the strain rate. But I'm not sure about the elastic portion. Okay, so we need to read more about it. Okay, so this is all about damage. Yeah. So basically, when we are modeling rock material and ceramics, and even sometimes, yeah, rocks and ceramics like granite, for high strain rate problems like impact problems, we use this material model. Okay. And there are some articles in which you can find the material properties for this in this model. Okay, let me just search quickly because I have that paper, so I know it's open source. Yeah, this is the one by Cronin. And we have a list here of properties for different ceramic or glass material. Okay, so this is in the format of material Johnson Holmquist ceramics. We have A, B, C, M, N, the pressures, and we have the damage. We have K1, K2, K3 in beta. So it's the same here, A, B, C, M, N. We have K1, K2, K3, and we have D1, D2, which is the damage. Okay. Okay, the person who asked the question has disappeared. Anyway, he asked the question long time in Facebook, and I had a look at it, but I wanted to reply, then I got carried away and totally forgot. Okay, so any more thing? Any other questions? I think we cannot.
For me, no questions anymore.
Okay.
It was very interesting.
Okay, good. Oh, I hope that you learn a lot and you can practice on your own.
Yeah,
And
yeah,
you
certainly.
you have been practicing, and I can see that. So
Yeah.
that will be in the DYNA examples for the ICFD. There are too many examples, so I think you can get a lot of information from there.
Yeah. I already looked at the examples. from Dynamo, and that's very interesting too. Yeah, yeah.
Okay. So since we do not have anything else, I think we can finish for today and finish the workshop. And we will be in touch. You have my Facebook, or you can find me on Facebook. You have my email.
Yeah,
So thank you very much for joining and for participating. Actually, many have registered.